Hello and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about a mass on the end of a spring as a simple harmonic oscillator. Now, this is a continuation of my discussion of simple harmonic oscillations and periodic motion. The mass on the end of a spring is just a special case of the simple harmonic oscillator. Recall that the simple harmonic oscillator is a system which is described by the equation A, that is the rate change of the position, plus omega squared x is equal to 0, where omega is some constant. Sometimes we write this as an omega naught, sometimes we write it as an omega. It just needs to be some constant. You'll recall further that omega is going to be defined for our system as 2 pi divided by the period. So it is a type of periodic motion, and the period is given by t. So for a periodic motion, you have a period that describes how long it takes to complete one complete form of that motion, one whole oscillation or one whole cycle. So period t is time to complete one cycle. And this is, in some sense, one of the more important characteristics of the simple harmonic oscillator, this period or amount of time to complete one cycle of motion. Omega is alternatively equally important, sometimes more so just because of how it shows up in the equation. Finally, you'll recall that the position versus time for this for the simple harmonic oscillator is not a constant acceleration type equation, but instead has something like x is equal to x naught or x max times the cosine of omega t plus phi naught. It can also, for what it's worth, be described using two different values of displacement and a sine and a cosine. But for physics 1 purposes, physics 2 purposes, introductory physics purposes, I prefer this form of the equation because we know what each one of these three things tells us for that system directly. Basically, you have an amplitude, you have a frequency, you have a phase. So what about this mass on a spring system? Well, the mass on the spring system basically assumes that you have a spring like this, which is fixed on one end, and you have a mass, m, which is on the other end of it, and which is free to move up and down. So we expect this thing to be moving up and down. Now, if we were to do the sum of forces for this system, sum of forces would basically look like k times, let's say, delta x, the amount that the spring is stretched or compressed by. And so if it stretches downward, then I get a force upward. And so for this particular system, maybe we would say something like k delta x minus m times g is equal to mass times acceleration. Now, let's use a little trick. So, trick. Since this force varies linearly and this one's constant, replace the force side, replace these with k times x, where x is position relative to the equilibrium position. And actually we want to replace it with a negative k times x, as it turns out. So x is position relative to the equilibrium for the system. So what this basically does is that instead of having to take into account gravity, I kind of am incorporating it into part of the spring's force is nullifying gravity on the system, and so we only really care about whatever's left over after that part of the spring's force has canceled. And so if the mass is higher up, that would be like a positive x, but the spring would be pushing downward, and so essentially you'd have a negative kx from there. And if the spring is pulled further down, then the spring should be pulling upward, or you should have a net upward force. And so you have a negative x and a positive value, therefore, of negative kx, or a positive value of force. Be that as it may, if we change this equation around, what we end up getting is that k times x plus m times a is equal to 0. So I basically just adding this negative kx term, I'm adding a plus kx to both sides of this equation and then grouping everything that's not 0 on one side. Or alternatively, I could write this as ma is equal to negative kx, and that would be in terms of just leaving this alone. Well, we expect our equation to have the form a plus omega squared x is 0. So what that means is that I expect to have a is equal to negative omega squared x, but if I divide both sides of this equation by m, I have a is equal to negative k over m times x. So putting these two statements together, these taken together imply that omega squared is k divided by m, where k is the spring force constant. So that's kind of an important equation. We could rewrite this again as omega is equal to square root of the spring force constant divided by the mass of the system. And similarly, that means that the period t is 2 pi times the square root of the mass of the system divided by the spring force constant. Again, this is important enough to be boxable. As far as the spring itself goes, remember that the simple harmonic oscillation equation says that x should be x naught times cosine omega t plus phi naught. Well, we now have an omega term right here that we've solved for within this system. So what's the other stuff in this equation represent? Well, this right here would represent maximum displacement. So this is the amplitude, maximum displacement from equilibrium. And so this is essentially akin to saying if the system is at equilibrium and I grab onto the mass and I raise it by, let's say, like 5 centimeters, and then I simply release it at rest, so it does this thing, well, then this term right here becomes that 5 centimeters that I displaced it from initially. This right here, again, is phase offset, and what it basically means is my initial speed is v initial equal to 0, and specifically is the initial velocity equal to 0. If yes, then the phase term phi naught will also equal 0. If no, then we need to know the direction and magnitude of that velocity, or else we need to know a position at some later time, preferably while also knowing what the frequency is in order to fully solve for phi naught. All right, so let's work an example to end today's video. All right, so we have a simple harmonic oscillator system with a spring and mass. We know that the mass, m, is 1.6 kilograms. We know that the spring force constant, Ks, is 14.4 newtons per meter. We're even given the initial displacement, x naught. We want to know what the period of oscillation is. Well, t should be 2 pi times the square root of m divided by k, or ks if you'd prefer. So that is 2 pi times the square root of 1.6 kilograms divided by 14.4 newtons per meter. Okay, so what does that come out to? That comes out to a total of 2 divided by 3, or 2 over 3.0 pi seconds. So if you want to calculate that to a number of seconds without the pi in, then that ends up being 2.0943. So let's call that 2.1 seconds. So that should be the period of oscillation for this particular mass and spring system. You'll notice that at no point did I use the initial displacement. It's because the initial displacement should not, so long as we're in the linear elastic regime, should not affect the period of oscillation. And as a general rule, we assume that we are in the linear elastic regime. That is where F equals kx, or F equals negative kx, is a valid equation. So if I were to change the problem to, say, 7.8 centimeters, in other words, I double the initial displacement, what would happen to the period? Well, you might pause it and think about that before I answer, but if you don't want to do that, or if you have paused it already and are now back for the answer, if I double this initial displacement, it should not have any effect on the period. The period should remain 2.1 seconds. So that's all for today's video. Hopefully you learned something from it, and thanks for watching.